Hello and welcome. We're going to pick up where we've left off. You'll remember that we've been working our way through chapter three of this book. And in particular, we were talking last time about the quantization of energy. That's section 3.5. And then we're going to continue with that and move on to section 3.6 on the color index. Many of you were at the last lecture. Some of you weren't. It's okay either way, because we're going to review what we were doing at the end of the last class and then finish the example problem that we were working on in 3.5 before we then move on to section 3.6. And then after we're done with chapter 3, we're going to be skipping chapter 4 and working our way into chapter 5 on the interaction of matter and light. So last time we talked about the Planck function. Remember, the Planck function is the intensity of light versus wavelength or versus frequency for a black body. And so qualitatively, this is what a black body curve looks like here. The B sub lambda we write when it's a function of the wavelength lambda. B sub nu, we'd write it that way when it's a function of frequency nu. Remember that lambda times nu is equal to c, the speed of light. So these two functions are intimately related to one another. And in fact, we derived the connection last time. Now, this was equation 3.22, the B sub lambda. Notice it's got a 1 over lambda to the 5th, and it's got this exponential in the denominator. And here we also had equation 3.24, which is the B sub nu. It's got a 1 over nu cubed, and it's got that exponential in the denominator, in both cases -1. And we showed that connection. Now, note that they are both functions of temperature. So the black curves that I've drawn here in each case are for a constant temperature. You can think about a single object, a single star, say, with a uniform surface temperature that's emitting like a black body. So in the short wavelength regime, that's the high energy photons coming out. Long wavelength, that's low energy. Over with frequency, high frequency is the high energy. Short frequency is the low energy. Now, we mentioned in the previous subsection 3.4 that there is Wien's law that tells us where the Planck function peaks, lambda sub max, that is, as a function of temperature. So we drew many different Planck functions, different for each temperature, one for each temperature. And we saw that lambda max, where it peaked, got less and less as the temperature got more and more. And we quantified that with Wien's law. This is the equation 3.15 in your textbook, that lambda max times temperature is a constant. It's 2.9 times 10 to the 6th nanometer Kelvin. And so as lambda max goes down, temperature goes up, or vice versa, in such a way that their product remains the same. Now, we didn't derive that. That's going to be one of your homework problems for set number 4. But we did talk about how you would derive that. Whenever you're looking for a peak of a function, remember that you would look, as you told me, for when the function is at a slope of 0, right? Because that's when you would have a maximum or a minimum and extremum in general. And so what we're looking for is where does the derivative equal 0? I've gone ahead and used partial derivatives here. If you haven't had multivariable calculus yet, you can, for the sake of this discussion, consider those little script d's, the same thing as normal d's, but just remember that temperature is also being held constant when we do the derivative. The script d's are just a reminder to us that we're keeping temperature constant as we do the derivative. And so we'll set that derivative equal to 0, evaluate the derivative, evaluating it at lambda equal to lambda max. That is the condition for lambda max. So when you do that, that's how you get Wien's law. So Wien's law is tied to the functional format of this. You're going to show that mathematical connection on your homework. But at the beginning of today's class, we'll pick up right now at what we were doing at the end of the last class, which is a very similar problem. The mathematics is very similar. We are going to look for where the peak of B sub nu occurs and solve that and find a relationship between nu sub max, the frequency where it peaks, and temperature. And so when you're working it out on your homework to derive Wien's law from the Planck function, you can follow similar steps, although the details will be slightly different. So this is really just problem 3.13a on page 82 of your textbook that we're working right here to find nu max as a function of temperature, that is the frequency for which B sub nu attains its maximum value. So the idea is, as we said, you want to find when the slope is equal to 0. Now, for the sake of simplicity, I'm not going to, for a while, write nu max. You can think about what we're doing here as evaluating this derivative at nu equal to nu sub max. But I don't want to have to keep writing that, and I don't want to have to write nu max on everything. So later on, at the end of the problem, when ultimately I am almost to the finish line, I will go ahead and start writing nu max again. But for now, I'm just going to write nu. And we'll remember that we're differentiating with respect to nu. There, the nu is a variable. But after we've done the derivative, we're going to evaluate it at nu equal to nu sub max. So here is our B sub nu up here, equation 3.24. That's the thing that we are differentiating, that we want to put equal to 0. And I note that there's a 2 at h and an over c squared up there. And so 2h, c, those are all constants. H is Planck's constant, c is the speed of light. And so when you're differentiating a constant times a function, you can float that constant out in front of the derivative. And that's what I've done here. We're still reviewing some of the steps that we had at the end of the last class. Most of what's on the board here, in fact, we did at the end of the last class. We did everything up to about what's above my hand here. But now we're taking partial by partial nu, that is the derivative with respect to nu, of, and then everything else that was in our B sub nu expression. So nu cubed times this thing in parentheses, the denominator. And since it's the denominator, I'll go ahead and just write it as the that thing in parentheses raised to the -1. Now, we wrote out the mathematics of differentiating this last time. Let's just make sure we understand where all the terms came from. We were using the product rule of differentiation. Remember that the derivative of a product of two functions f and g is the first function f times the derivative of the second function g plus the derivative of the first function f times the second function g. So fg prime plus f prime g, where prime is the differentiation indicator. And so that's what we've done here. I'm thinking about this as two functions that are being multiplied together. The first function f is nu cubed. The second function g is that denominator raised to the -1 power. And so, okay, let's look at the mathematics of it. There's the first function f. Then I want to multiply it by the derivative of the second function. And a couple or few of you, it's been a minute since you did your calculus, but you're going to need to know the chain rule of differentiation. And I'm going to talk it through with you here, but also if you need some practice on it, for better or worse, you know, everybody seems to know that there exists these step-by-step calculators out there like Symbolab, for example. That symbol means there exists. So if you need to review how to do things like the chain rule, go to symbolab.com and do some chain rule examples. Here, what we're doing is we're differentiating this function g with respect to nu. But nu is hidden inside the exponent of this e here. It's also in this difference of two terms raised to the -1 power. And so we need to use the chain rule repeatedly to be able to do this derivative. At the outermost level, we have something raised to the -1 power. And remember, when you differentiate x to the n with respect to x, you get n times x to the n -1. You bring down the exponent. So there, -1 is out front. Then you have what you had before, the thing in parentheses, raised to 1 less power. So -1 is raised to the -2. And then from the chain rule, you have to multiply by the derivative of the thing that was raised to a power. And so the derivative of the thing being raised to a power was this denominator, e to the h nu over kt minus 1. And the derivative of that is just the exponential e to the h nu over kt. And then we have one final time, one final layer of the chain rule, one more link in the chain. You have to then differentiate by the argument of the exponent, because we weren't differentiating with respect to h nu over kt. We're differentiating just with respect to nu. And so the derivative with respect to nu of h nu over kt gives us this h over kt. So we've done the first f times the derivative of the second g. We've done half of the product rule of differentiation. Now we need to do the second derivative of the first times the second. And so here's the derivative of the first. Nu cubed is 3 nu squared. And then there's g. We just write out what g was, and we have completed that line. Now, at this point, we want to do some simplifications because it looks kind of messy, and we're trying to remember solve for nu. And so the first thing that I'll note is that there are some commonalities between the two terms that are being added together here. Like they both have nu to a power. They both have the denominator raised to some number, -1 or -2, depending on whether you're talking about the second or first term respectively. And so you could think about factoring out those commonalities, and because it's equal to 0, then dividing out those commonalities and just concentrating on what remains. The way I'm going to do it here is I'm going to multiply both sides by that denominator squared divided by nu squared. Why do I do that? Well, I don't like having things down in the denominator. And in my mind, this thing to the -2 is that thing squared in the denominator. I'd like to get it up to nothing, 1 rather, or out of the denominator at least. And so if I've multiplied both terms by that denominator squared, this thing in parentheses is just going to be that thing to the 0, which is 1. And this thing, at least it comes up, it'll have a power of 1 rather than -1 after I've multiplied. And I'm also going to divide by nu squared. And so that would get rid of the nu squared here, and it would take this down to nu, to the first power. Now, because I'm multiplying both sides of the equation by that same thing, I need to worry about the left, but the left is just 0. And if you multiply 0 by anything, that anything is not going to be 0, and or 1 over 0. It's going to be nice and well defined. And so we just get 0 again on the left-hand side. And so this is what it reduces down to. It starts to now look simpler. Look, there's the minus right here. Nu cubed became nu. There's the e to the h nu over kt. I had the h over kt that goes to there. And we said we multiplied by the right thing to get that to be raised to the 0. Likewise, this 3 becomes that. The nu squared went away because we divided by nu squared, and then we multiplied this by that thing in parentheses squared, so we just have it to the plus first power here. That's not a mistake. That's a +1 power implicitly that we're raising that to. And now we can make this simpler still by saying, hey, look, there's a combination of variables which appears repeatedly in this particular expression. In particular, look at what we're raising e to the h nu over kt. Well, there's also an e to the h nu over kt here. And if you look, there's an h times a nu over kt here as well. So if we define this variable x, which is dimensionless, by the way, h nu is an energy, kt is an energy, it had better be dimensionless because we're taking e to that quantity, and you always take e to a dimensionless quantity. If we introduce this variable x, which is h nu over kt, then actually this starts to look somewhat simple. We have negative x from the h nu over kt, e to the x in the first term. And in the second term, we have 3 times e to the x minus 1. And now there's just one variable in this equation, one thing, x, that we can imagine solving for. Now, unfortunately, try as you might, because this is what's called a transcendental equation, there's no analytic way for you to isolate x and to say x is equal to something which does not also involve x. And so this has to be done either numerically or by some iterative procedure. One could, for example, solve for an x in terms of other x's, make a guess at what x is, plug it in on the right, you get a new value for x, plug that new value back in for the right, you get a new value. There's an iterative approach that you could take, but we're just going to solve it numerically. And what we're going to do, in fact, is I'm going to show you a nice kind of tool that you can get online, Wolfram Alpha, and make use of for solving things numerically, even if you don't have a lot of prior experience. And so in particular, let's say that you go to wolframalpha.com and let's start with something simple. Let's say you just wanted to solve the equation 0 equals x plus 1. You don't have to be too specific with the syntax. I mean, you just use English if you can, like solve this for me. And, you know, you don't even have to say solve it for x. It's smart enough to know that you're solving this for x. So if I run something like this, it takes a moment and then it says, oh, x equals -1. Of course, we knew that x was equal to -1 for that simple example. But the point is that you could type more complicated examples in there, like minus x e to the x plus 3 e to the x minus 3. That's the same thing I have on the board. In fact, let me write it even more explicitly like what I had on the board by writing 3 times the quantity e to the x minus 1. And so now if I go and I solve this, scroll down, I see x is 0, but that's not the solution we want, or 2.821. And that is the solution we want. How do we know which of those solutions we wanted? Well, you see what was happening there is we were finding both locations where the slope was 0. And the slope is equal to 0 right there at nu equal to 0. But that's not a local maximum. That's actually a local minimum, or at least as you approach it from the right, that is from positive news. I don't know what negative news exactly mean, unless they mean your wave's moving the other direction. But it's not a maximum for sure. And so we are looking for this 2.821 is what x would be. And if you're ever not sure about that, I mean, it's simple enough. Now that we have a guess at approximately what x is, you could plug it in there, minus 2.821 e to the 2.821 plus 3 times quantity e to the 2.821 minus 1. You'll find that it is almost precisely 0. Not quite, because it's an irrational number. You saw that Wolfram Alpha gave us more digits than the 2.821. But the more digits you decided to keep, the closer this right-hand side here would be to evaluating out to 0. So what do we do with this? What does this mean? X equals this particular dimensionless number. Well, remember how we defined x way back when? It was h nu over kt. And at this point, I'm going to remember again that I am evaluating the derivative at the location where the slope is 0, and I am calling that particular frequency nu sub max. So for x, I will write h times nu sub max over kt. That's what 2.821 is. And I'm at this point done. I've done all the hard work, but now I get to do the fun little unit conversions and write it in a different way, in a different final format. Because the question did ask us to find nu max as a function of temperature. So I'm going to solve for this nu max right here. I multiply both sides by kt over h. So nu max is 2.821 times kt over h. And if I like, I can plug in values for Boltzmann's constant k and Planck's constant h. Right? 2.821 times, here's Boltzmann's constant. 1.381 times 10 to the minus 23 joules per Kelvin. And I wrote out the word Kelvin here because I didn't want to confuse it with the Planck, with the Boltzmann constant itself, K. It would be a capital K, Kelvin. Then we divide by H, 6.626 times 10 to the minus 34 joule seconds. And so I see that in the numerator, there's a joule. In the denominator, there's a joule. So those make a ratio of 1. And thankfully, I have temperature here that's left over from that temperature there, which is being divided by this unit of Kelvin. And so in the end, the units I'm left with is 1/seconds. Now, 1/second is a hertz. A cycle per second is a hertz. And so you can see the dimensions I'm left with are hertz per Kelvin. That, as I said, was multiplying by being multiplied by temperature. And all the numbers work out to be 5.88 times 10 to the 10. So you see, this is the equivalent of Wien's law back here. Just like lambda max times T is a constant, well, nu max divided by T would be a constant. And you might think that because lambda times nu is equal to C, you might think, but you'd be incorrect, that lambda max times nu max is equal to C. But that's not the case. The mathematics that we went through here, we really have to do. If all we knew were Wien's law, that would not be enough, right, to be able to tell us where this function peaks. All right, so that is it for that example problem, 3.13a. Hopefully you can refer back to those steps as you're working through your homework problem where you're deriving Wien's law. What I'd like to do next is to share screen again and to show you some slides about section 3.6 on the color index. And so let's go ahead and bring those up. These slides will be placed on Canvas so that you can access them there. But in section 3.6, we're going to talk about two main things. We're going to talk about the what filters are, and then we're going to use that to connect color index. And then we're going to do some example problems where we talk about things like bolometric correction and how that allows you to transform from a visual magnitude to a bolometric magnitude. And we'll do an example problem that ties together a few of the ideas that we're looking at this chapter. So you see in the upper left of the screen there that there is a wheel that has been shown to us that has different filters on it. What an astronomer does is they put this wheel at the base of their telescope, and then the light that they're observing goes through one of these filters. You take an image, and in a sense, every image that you take is a grayscale image. It's grayscale in the sense that, you know, you're just letting a certain type of light through. Like, for example, let's say for the sake of argument, you're using the V filter. The V filter is right in the middle of the visible band. You can see it peaks around 6,000 angstroms or 600 nanometers. So this little green curve here labeled V, it shows us that it's letting through 100% of the light at the peak there. I guess the peak is not quite 600. It's maybe actually closer to 500 nanometers, but it's definitely between 500 and 550 nanometers where it peaks. And so if you go to too short of a wavelength, then that light, the blue light, the ultraviolet light, whatever, just doesn't make it through the filter. It's filtered out. Or if you go to too high of a wavelength, above about 700 nanometers, 7,000 angstroms, that would be filtered out. And so that's why this looks green. I mean, it's just like a little green sheet of plastic or glass, right, that lets through specific wavelengths of light. It's green because the other colors don't get through. The green is what's getting through, right? And it's a function, but you can approximate it as saying, well, I'm letting all the green through, but none of the other colors. The blue filter lets through, as you can see here, blue light. The R filter lets through red light. There's also U for ultraviolet. There's I for infrared. There are many different types of filters, but these are some of the most common. And you could imagine taking that filter wheel on the base of your telescope. You do an observation in one of the filters. You turn the wheel. you observe the same object in another one of the filters, you turn the wheel, you do an observation in maybe a third filter, and then you have three separate, what individually you could make grayscale images, but then you false color them. Why false color them? Well, maybe one of the filters you used was ultraviolet, and there is no true color associated with ultraviolet, that your eye can't see it. So maybe because it's short wavelength ultraviolet, you might make that blue, and you might make some infrared image that you took of your object red, and then maybe you'd make a visible green, and then you could superpose the blue, the green, the red, and make some beautiful color image from those three filtered images. And so that's often what is done in astronomy when you see these different colored images. And it doesn't always have to be done with the same telescope either. You might have the Spitzer telescope, the Hubble telescope, and the Chandra X-ray telescope all taking an image of the same object, but in different wavelengths, and you could superpose their individual images into one beautiful color image. So filters allow us to control what band of waves, what range of wavelengths we're looking at. Now, if you talk about the energy over all wavelengths, then you would be talking about measuring something called a bolometric magnitude. If you think back to the Planck function just for a moment, and imagine that we were looking at some object that had this distribution of intensity for its light, this spectrum. And if you were looking at it through a V filter, depending on what object it is, maybe that's the range of wavelengths that you're seeing. So with that one image, with that one filter, you're not gathering observational information about what the spectrum looks like over here and what the spectrum looks like over here. You're just getting information about one portion of the spectrum. And if you used another filter, you'd be looking at another wavelength regime. You get information from some other portion of the spectrum and so on. Now, ideally, one might want to have what's called a bolometric magnitude. That is to take into account the energy of the light from all wavelengths. And how do you do that? Well, in practice, you don't. In practice, you measure in at least one filter, and then you make corrections to estimate what the bolometric magnitude would have been. And we'll talk about that. But you can, in principle, imagine that you could do this, that you could measure the intensity of the light at all wavelengths, and then use that as an indicator of determining what this bolometric magnitude was. So let me go back to sharing this and point out that if you are measuring with the V filter in particular, then we would call the magnitude just capital V, which is the same thing as lowercase m sub v. So this is a new notation. It's the notation that's used in your textbook. It's a common notation. If you have to do an example problem on your homework and you see like magnitudes listed in Appendix F that you're referring to, you'll see things like capital V. Capital V is the same thing as lowercase m sub v. In other words, it's the bolometric, it's the apparent magnitude in the visible, with the V filter. If you see a capital B, that's the apparent magnitude in the B filter. We call that the blue magnitude. If you see capital U, it's the apparent magnitude, lowercase sub m, in the U filter. And so you could have, for a single object, you could have capital V, which is an apparent magnitude, and then capital M sub V, that would be an absolute magnitude, right? The apparent magnitudes, remember, are the measure of how bright some object appears, now just in these specific filters like V, B, and U, for example. Now, if we take a difference between two apparent magnitudes, you get what's called a color index. So let's just say what the color index is mathematically at first, and then let's start to think about what it means and what it tells us. So an example of a color index would be U minus B. You get the apparent magnitude in the U filter, you subtract from that the apparent magnitude in the B filter. That's the color index U minus B, one number minus another number. And so you can take into account that as long as you measure the object in the two filters from the same distance, which you would always do, you would get the same difference. But the reason I'm pointing this out is that you could imagine taking the object that you're looking at and where however close or far it may be from you and moving it to a distance of 10 parsecs in your mind. In this thought experiment then, at that new distance, the new apparent magnitude would be equal to the new absolute magnitude, which is the absolute magnitude. And so regardless of whether you were talking about how much the apparent magnitude changed in the U filter or the B filter when you moved it to a distance of 10 parsecs, it would change by the same amount. By the inverse square law of light, the light would get dimmer at any wavelength regime that you were considering, or brighter by the same amount, right, as you moved it to 10 parsecs. This is all just to say that if you want to calculate a color index, you can take the difference between two apparent magnitudes, like we do on the left-hand side here, U minus B, or if it's more convenient because maybe you've looked up and know the absolute magnitudes, then you could take the difference between the two corresponding absolute magnitudes. You just couldn't take the apparent magnitude in one filter minus the absolute magnitude in the other. That doesn't make sense. But as long as they're both apparent or both absolute, their difference is going to give you the color index. Now, what does this color index mean? Well, as the name implies, it's giving you information about what the color of the object is. And so let's think about it. Let's say U minus B is a negative quantity. Remember what negative magnitudes mean. Negative magnitudes are getting really bright. The sun is negative 27, right, for its magnitude because of how bright it appears in the sky. And so if the difference in magnitudes U minus B is negative, it means in a sense that the U light is stronger than the B light, loosely speaking, right? Because you had, in the end, U being smaller than B, so that U minus B was negative. And so the ultraviolet light, there's more of it. There's more U than there is B, blue light. And so the way that you get something that has, you know, more ultraviolet than blue, and you're saying, well, I'm talking loosely, I know, but how do you do this comparison? What does it mean to have more ultraviolet than it means to have blue? Use Vega as a reference point. That's how these scales were initially calibrated. And to a very accurate approximation, you know, Vega has a lot of zeros on all of its values. Its color indices are 0, you know, its visual magnitude is close to 0, bolometric magnitude is close to 0, a lot of zeros associated with Vega. And so if you are talking about U minus B being negative, that means it's hotter than Vega. It has a larger ratio of ultraviolet to blue light than Vega does. And so if I stop sharing screens here for a second and we look back at our Planck function, you know, what does it mean to have a large ratio of ultraviolet to blue light? Well, to talk about that, it'll be helpful to draw on the same graph two different spectra. So let me draw a spectrum for a hot star, and let me draw a spectrum for a star that's not as hot. And so they might look like this. And so this, of course, is the hot star. This is the star that's not as hot. I'll just call it cool. And so the idea is, let's say for the sake of argument, that this is an ultraviolet wavelength right here, and this is a blue wavelength. You see how the ultraviolet is a little bit larger than the blue in that example. But if you go to the hot star, the ultraviolet is proportionally a lot larger than the blue for the intensity at that particular wavelength that we're talking about. So what I'm saying is that as you go to U minus B, which is more and more negative, you would be working your way up to higher temperatures, that is to curves like this, for which the U light is much larger in intensity than the blue light. Now, if you go the other way, and I'll start sharing screens again here so that we can look at the next example and think about U minus B being positive, well, then there's a lot of blue light compared to infrared light, right? Because remember, smaller magnitudes are brighter. So this would have to mean that B was smaller than U in order to make U minus B be positive. And so if we think about drawing now a third curve on a diagram like this for a very cool star, it may be peaking off to the side here. And you see how the blue is actually brighter than the UV. So what would be normal, where you would have U minus B equal to 0, would be whatever Vega's curve looks like. The curve of a 9600 Kelvin black body well approximates Vega. And then if it's a lot more in UV to blue, you would get a negative U minus B color index. And if it's less than that, you get a positive U minus B color index. And so if you plotted if you listed a table of a bunch of stars, U minus B indices, the ones that were more negative are going to have higher surface temperatures than the ones that are 0 and more positive. Let's go ahead and share screens again and continue on. U minus B is not the only color index that's out there. Here's another common one, B minus V. And again, you could take B minus V, that's the apparent magnitude of B minus the apparent magnitude V, or MB minus MV, where capital M's tell you that we're using the absolute magnitudes. So as a thought question, let's just take as a given that the sun has a color index B minus V of 0.65, whereas Sirius A, the brighter component in the binary Sirius system, has a color index of 0.0 for B minus V. So which of these emits bluer light? And what we mean by bluer light is preferentially shorter wavelength light. That is, a spectrum would peak at shorter wavelengths. You can pause the video here if you wanted and think about it, but we're going to go forward and have you step through the thought process. So if you want to think about it, remember that smaller magnitudes are brighter. So as B minus V goes down, that means the star becomes more blue, because going down means that, okay, the B is becoming more and more and more important. And B is blue, V is visible or visual right in the middle of the visible wavelength bands. And so if the star is becoming more blue, that means that Sirius is going to be the bluer of these two objects. So in actuality, Sirius is blue-white to the eye. We'll discuss that a little bit more later, but to foreshadow what we're going to say is, well, we're kind of near the peak of the spectrum, and if you're talking about the visible wavelength band, but there's certainly more light on the blue side than there is on the red side. But you do still have a fair amount of intensity throughout all the colors of the rainbow, which mixes together to give you white light, but maybe a little bluish tint to it to the eye, like stars that have temperatures of around 10,000 Kelvin, such as Sirius. So I was mentioning before that you really usually just observe objects in filters, that there's no one instrument that can measure the intensity of the light at all wavelengths and thereby give you a way of calculating the bolometric magnitude. So how do you do it? Well, if you've studied enough stars with enough different filters, you can start to see patterns that stars of certain types would have a bolometric magnitude that differ by such and such an amount from what is in the V filter. And so that difference between the bolometric magnitude and the V or visual magnitude would be what's called the bolometric correction. The idea here in these equations that you see is that you could measure the brightness as it appears, the apparent magnitude in the visual, and add to that a bolometric correction that you would look up from some table. Now, we haven't talked about in this class yet the different spectral types of stars. We'll learn later that stars can be classified according to their surface temperature and size. There will be spectral types of O, B, A, F, G, K, M. There'll be different luminosity classes depending on the evolutionary state. But for now, all you need to know is that you could look up, and if you can identify what type of star it is, you could say, okay, well, now I know what bolometric correction I would use for that particular type of star, right? Sirius is an A0 main sequence star, or an A1 main sequence star. And so that would tell me what bolometric correction I would want to use. And so if you know that bolometric correction, you could either add it to the apparent visual magnitude to get M bol, the apparent bolometric magnitude, or you could add it to the absolute visual magnitude if somehow you had that or saw it in a table to get the absolute bolometric magnitude. Questions or comments on this? I guess I can't say that. Here's an example that we're going to work through. I'll go ahead and I'll work through it on the blackboard, but let's just see. We're given a bunch of information about Sirius A, and these are the things that we want to calculate. We're told that the bolometric correction is -0.1, the color index is 0.0, the apparent visual magnitude is -1.5, the surface temperature is 9,900 Kelvin, the radius is 1.19 times 10 to the 9 meters, the distance is 2.7 parsecs, and we want to calculate this list of things. The blue magnitude B, that's an apparent magnitude, by the way. You can tell that from the notation, capital B. Apparent bolometric magnitude, M bol, the luminosity L, the distance modulus M minus capital M, the absolute bolometric magnitude M bol, the flux of light at the star's surface, the peak wavelength lambda max, and the part of the spectrum that peak wavelength is in. So this will give us a chance to review some of the ideas that we've introduced in today's class so far, as well as from earlier in the chapter. Okay, let's go ahead and work this on the blackboard. Bam, better than TikTok. We've got already here written out for us the quantities that have been given to us. And now let's go ahead and work this problem. In the first part, part A, we're trying to figure out what is the apparent blue magnitude. And if we look back, well, we've been given information about B right here. And in particular, if we add V to both of the sides of that equation, the equation B minus V equals 0, we find that B is equal to V plus 0.0. And V was -1.47. And so, yeah, there we go. We figured out what V is. You'll be able to do similar kinds of things on your homework as well. Now, in part B, we're asked for the apparent bolometric magnitude, lowercase m sub bol. And remember, the whole purpose of bolometric corrections were that you can take what you measured in the V filter. So there's the apparent magnitude in V. As a reminder, that's the same thing as lowercase m sub V, but it's the more common way of writing it because you only have to write one letter rather than two. And you add to that the bolometric correction. And we know that V is 1.47 in the negative, plus negative 0.1. So this is about negative 1.57. So that's the answer to part B. Then in part C, we're asked for the luminosity. And okay, well, I see we've been given this temperature. That's the temperature at the surface and the radius. So why don't we use this expression we talked about in the last class, that luminosity is flux times area. The area of the surface is 4 pi r squared, and the flux is sigma t to the 4th. And so now it has become a plug and chug. We can plug in for the radius 1.19 times 10 to the 9 meters. That's going to get squared. Our Stefan Boltzmann's constant is 5.67 times 10 to the minus 8, and that is in watts per meter squared per Kelvin to the 4th. And then that gets multiplied by the temperature, 9,900 Kelvin to the 4th. And if we look at this dimensionally, or more precisely with the units, we see here this K and this K make a ratio of 1, because here's K to the 4th, and this was also K to the 4th. So they all make a ratio of 1. And in addition, we have a meter squared there, once that gets squared out, which would cancel with the meter squared there. And we're just left with watts, which is joules per second. That's the correct SI unit for luminosity, energy per time. Now, all of this stuff here, if you ask your calculator to evaluate it, works out to be 5.4 times 10 to the 8th watts per meter squared. And so with that as an intermediate value, we additionally multiply by 4 pi, this number here squared, and we end up with 9.7 times 10 to the 27 watts. Now, that's fine, and if you like, you can put a box around it because you've answered the question, you've given the luminosity. But I've seen on your homework, and I know in practice, that it's very useful if you go and you change units to something more astronomically reasonable, so that you realize whether or not your answer may make some sense. I mean, if in a problem you solve for the speed and you get some answer which is 100 times the speed of light, but you don't think about what the value meant, then you're not giving yourself the opportunity to catch your mistakes and to understand the physics better. So I'm going to convert this answer to solar luminosities. I'd like to know how many times brighter is Sirius than the sun. See if it's something reasonable. If I find that it's no brighter than, a 60-watt light bulb, obviously it's a lot brighter than that, then I know I've found something ridiculous. Anyway, let's do it. How do you do it? Well, you convert units by multiplying by 1. And so in particular, the luminosity of the sun is 3.85 times 10 to the 26 watts. So it's not that much less than the value we had. So this is looking potentially quite good here. And then L solar in the numerator is the same thing as that 3.85 times 10 to the 26 watts in the denominator. We've multiplied by the term in parentheses there, which is 1. So now we have done the conversion. We get 25 solar luminosities. And so indeed, that is a reasonable brightness or luminosity rather, for the brightest star in the night sky. You see, Sirius is not that far away, only 2.7 parsecs away. So on the order of 10 light years, and a parsec being 3.26 light years. And it's also, pretty bright, 25 times brighter than the sun. So the combination of it being pretty bright and pretty close makes it the brightest star in the night sky. All right, so in part D, we're asked to find what the distance modulus is. And a distance modulus is little m minus big M. And those could be in any filter or bolometric. as long as the two m's are taken in the same way. And so that is equal to 5 times log base 10 of d per 10 parsecs. So it's plug and chug. If you know the distance, you can immediately get the distance modulus. And that's what we're doing here. You can also, if you ever know the distance modulus, solve for the distance. And so let's plug in for d. This is 5 times log base 10 of, well, 2.7 divided by 10 is 0.27. And the parsecs in the numerator and denominator make a ratio of 1. And then when I ask my calculator to evaluate this, this is negative 2.84. So that is the so-called distance modulus. Note that it's a negative number, which means that it's closer than 10 parsecs. The distance modulus of something right at 10 parsecs would be 0. The distance modulus of something larger than 10 parsecs is positive. And they go the same way. As distance modulus gets bigger, the distance to the object gets bigger, right? Okay, so those are parts A through D. Let's go ahead and clear the board and do parts E and on. All right, so M bol, the absolute bolometric magnitude, is what? That's what we're asked in E. Well, we could make use of this distance modulus that we were just talking about. In particular, it must be that lowercase m sub bol minus capital M sub bol is equal to that negative 2.84 that we had just found. And so we can go ahead and use our answers to part B and part D, which we've already used here, to find capital M sub bol. So capital M sub bol would be lowercase m sub bol plus 2.84. And then from part B, we found this was negative 1.57 for lowercase m bolometric plus 2.84. And this is equal to 1.3. Because of I want to avoid a cumulative round off error, I'll just stop at the 1.3 and not try to write any more digits, which I fear would be insignificant. Part F, we are asked for the flux at the surface of the star. Now, flux is energy per time per area. And energy per time is luminosity. And that luminosity is coming out from over an area, 4 pi r squared. And so if you want, you could at this point say, oh, I found the luminosity back in a previous part. Let me plug that in the numerator. I know the radius. Let me plug that in the denominator, plug and chug, get a value. But do remember that more directly, you could just use that. This is sigma t to the 4th. After all, the t was being treated as a constant temperature on the surface. And in fact, we already in the previous part calculated numerically 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th times that temperature to the 4th. And what we got back then was 5.4 times 10 to the 8 watts per meter squared. And so that's a very direct way to get to the answer. All we've done there is plugged in for T, as we had done previously back in part C of the problem. We're on to part G now. And in part G, we're asked to find lambda max. Wien's law is what allows you to find that peak wavelength, lambda max. And in particular, lambda max is equal to 2.9 times 10 to the 6th nanometer Kelvin divided by the temperature. And so, okay, that K there is Kelvin, not Boltzmann constant, of course. So let's rewrite the numerator. And then in the denominator, let's plug in 9,900 Kelvin. And so it's 2.9 million divided by almost 10,000. That's going to bring it down to 2.9 thousand nanometers. Now, that's 2.9 times 10 to the 2 nanometers. So that is 290 nanometers. And so that's the answer then to part G. And then finally, in part H, we're asked what wavelength regime is this in? Like, is it radio, infrared, visible, ultraviolet? What do you think? Answer quickly. Say it aloud in your rooms, in your pajamas. It's the ultraviolet, because remember, the visible goes from about 400 to 700 nanometers. And this is a little bit shorter wavelength than visible. And so the blue side, or the violet side, is at the 400 nanometers. A little shorter than that still gets you to the ultraviolet. You'd have to get all the way down to about 10 nanometers or less before you break into the X-ray regime. So this 200 nanometer is in the UV. When we write UV, we mean the ultraviolet. So now that we know where this peaks at 290 nanometers, we can be a little bit more precise about what we were saying earlier. What color would this appear? At least we can draw the spectrum a little bit more precisely. Now, I'll be honest that this spectrum is still an approximation. We're still just at this point modeling the star like that of a spectrum, which like that of a black body. Its spectrum would be like that of a black body. And in reality, the actual spectrum might peak at a slightly shorter wavelength, might have emission and absorption features in it, etc. But nevertheless, this is a decent approximation for what the spectrum of Sirius would look like. It peaks, let's say, right around 290 nanometers, as we've calculated. And so the visible range would be somewhere from about 400 to 700 nanometers. And so let's say that that's this range out here. This is the blue end, or the violet end, at 400. And this is the red end out at 700. And you see, there is light from all of the colors of the rainbow. It wasn't a really sharply decreasing function like what you would need to have if it were truly a blue star in the sky. There's still a fair amount of red light coming through. And so you do have this bluish white type color, the white from the mixture of all the colors, but since there's a little extra blue in there, it has a bluish tint. Truth be told, if you look at Sirius on a night sky, you sometimes see it flickering in colors, because the different colors, red, orange, yellow, green, blue, they all refract slightly differently in the atmosphere. And so you may be able to see a little twinkling with some colors around the edge of Sirius. All right, so that concludes our study of chapter 3. We're going to be moving on to chapter 5 on the interaction between matter and light. And we'll do that in a separate video. Okay, thanks. I'll see you in the next video.